Hello everyone, if you don't know me, my name is Filip Maciejewski. I'm a computer software engineer, joined Linaro in April 2023 year. Currently I'm working on the project which is about porting the database engine from X86 platform to ARM platform, and also doing the software performance optimization, which includes CMD vectorization of the source code. So that's my current role in the company. In my presentation, I wanted to present to you the CMD programming model and also the porting process from X86 to ARM. So CMD programming model is an efficient method of software parallelization. So in my presentation, I want to compare the ARM CMD, NEON and SVEx vector processing units against the X86 CMD SSE and AVXx vector extension. Okay, let's go to the next slide. So at the beginning, I want to introduce a little bit about the ARM, but you may already know the ARM history. So it was established as an Acorn RISC machine in the UK. Design initiated in 1983, first silicon 1985, 32 bits reduced instruction set machine inspired by Berkeley RISC. Okay. Does not produce their own chips. Companies customize based CPU for their products. So the main characteristic, Apple for its A4 design use the ARM which powers iPhone, iPad. These are some key facts. Okay. Next slide. ARM architecture as RISC features. We have fewer instructions, complex instructions handled via multiple simpler ones. Result is in a small execution unit. So we only have loads and stores to and from memory, uniform size instructions, less decoding logic, 16 bits in timed mode to increase code density. We also have some ALU features like conditional execution built into many instructions, which gives us less branches, less power loss to stall pipelines, and no need to branch prediction logic. We also have operand bit sheet supported in certain instructions. And we also have a support for 3 operand instructions. So as you may already know, all those facts in some history and introduction. Okay. So we also have some advanced features, as this is the main core of our presentation. So CMD, NEON and SVE to compete with X86 SSE and AVX at the high end in the segments like audio encoders, decoders, so MP3, also advanced encryption standard, SHA support, and also other multimedia processing sectors like video encoders, decoders, 2D, 3D graphics acceleration. These are just examples where you can take advantage of the CMD vector processing unit potential. Also on ARM, we have a hardware virtualizer, hypervisor mode, Giselle, security, no execute page protection, trust zone. Okay, and then we come to the core, so CMD. So first, I will give you some description of the CMD. What does it mean? It stands behind the single instruction which is executed on multiple data. So this is a form of parallel processing which exists since 1960s. The idea is rather than executing an array of operations by loop, we execute all of the array operations in parallel on different processing elements, arithmetic logic units. So here we have example, we convert a loop where we iterate over n elements. So it starts from 0, up to n-1, and in each loop iteration we increment the ith element of array A. This can be converted into a single operation, like just for A is equal A plus 1, which means that each element of the array A is incremented by 1. So this can be easily vectorized by the CMD instruction set. So there have been 3 approaches to CMD, so mainly the vector architectures, including matrix architecture, also multimedia CMD instruction set extensions, and graphics processor units. This is nowadays a common approach, so we also have a graphics processor units, like you already know, all the main vendors, like of course ARM Mali, Qualcomm Adreno, NVIDIA RTX GeForce GPUs, also AMD Radeon, and so on. Okay, so for the CMD we have like 2 views, two paths. So first path is we view the CPU as having a control unit and arithmetic logic units, processing elements, or PAEs in the figure here. So you can see on the figure how it looks like. The first view at the top right corner, and the second view at the bottom right corner here. So each processing element handles the datum from the array where the data is cached in the processing element local cache. Otherwise, the second approach is we use pipeline functional units rather than existing instruction on data simultaneously in each cycle. We start the next array operation in the functional unit pipeline. Okay, so its performance. So here we have some background and trends on high performance processors. So processor trends are like multi-core processing, so we have many cores, more and more cores integrated into the chip. So while the CMD, more and more FPUs are also integrated into the core. So on X86, the biggest competitors are AVXx, which is the vector size is 256 bits, and AVX 512 vector size is 512 bits. So all those instruction sets they operate on the 8, 16, 32 bits and 64 bits data types. So AVX2 was introduced with Intel Xeon, for instance E5, and AVX 512 is available in Intel Xeon E5 version 5, Skylake, later Skylake. So the problem of AVX programming on X86 architecture that there is no backward compatibility between the following AVX vector features. So for instance, the AVX code is not compatible with AVX 512, so you have to recompile the code. That's the problem on X86 architecture. So on ARM, we have a SVE vector extension, which comes with the agnostic programming model, which allows you to write portable code, which gets adapted at the execution time based on the hardware SVE vector size. We'll come to this later. So first, I want to introduce on ARM advanced SIMD NEON extension on ARM platform. So advanced SIMD NEON extension was introduced in ARM v7 instruction set architecture. So NEON instructions operate on 64 bits or 128 bits wide vector data. They perform the same operation on all data elements. NEON instructions operate on 64 or 120 bit wide vectors with a fixed point 8 bits, 16, 32 or 64 bits data, or floating point half precision 16 bits. floating point 32 bits single precision and floating point 64 bits double precision. So here you can on the figure you can see an example of the CMD data processing. For floating point 16 data NEON supports only conversion between floating point 16 and floating point 32 and floating point 64 bits data. So NEON comes with the register bank, dedicated register bank, register file. So NEON provides 256 byte register file, distinct from the core registers. So you can access the register file as 32 64 bits registers, which are denoted from D0 to D31, or 1620 bit registers, which denote from Q0 to Q50. So here we have some example of the NEON general data processing instructions. So like for instance vector convert between fixed point, or integer and floating point. So we can have some examples of the instruction syntax at the bottom left corner. So it's two operand instructions. So we have a source operand and a destination operand. It's also possible to execute the instruction conditionally. I don't want to go into the details of all the instructions because the instructions it's quite large. We also have some move variation instructions. Then we have examples of the NEON general arithmetic instructions like vector absolute difference and accumulate, vector absolute difference, vector add with and without saturation, of course vector subtract, so all kinds of arithmetic logic operations. Then I want to introduce the SVE, which is a scalable vector extension, which was introduced with ARM V8 processor architecture. So SVE is a complementary extension, does not replace NEON. So it's an extra additional vector processing unit and was developed specifically for vectorization of high-performance computing scientific workloads. So the scalable vector land increased parallelism while allowing implementation choice of vector land. So this is what I mentioned before. The vector land agnostic programming model supports the programming paradigm of write once, run everywhere, scalable vector calls. So when we implement the source code using the SVE vector extension, so we can choose whether we want to use an agnostic model, which is sizeless data types, or the fixed size. Yeah? The difference is between the program compatibility on different ARM processor architectures. Like it is mentioned, agnostic model allows you to build one code and run it everywhere on each platform. The fixed size SVE implementation can be run only on the CPU processor architectures, which support the specific fixed size SVE vector length. So the most popular nowadays, the most popular SVE vector size is 120 bits or sometimes 256 bits. So it introduces what's interesting in the instructions that it introduces gather, load, and scatter, store, which enables vectorization of complex data structures with non-linear access patterns. So we have also the most important feature is prediction. So pretty much most of the SVE instruction sets are fully predicated. So we have 16 SVE predicate registers. The SVE predicate register size is 1/8 of the SVE vector register length on the register size. So we also have extended integer and floating point horizontal reductions instructions which allows vectorization of more types of reducibility, loop carry dependencies. Yes. So we have add reduction instructions. We have minimum and maximum reduction instructions. But what is worth mentioning on most of the ARM processor architectures, which provides the SVE vector extension, the reduction instructions family, the instruction execution timings, they are rather slower than the NEON. That's based on my experience also working with my current project when we did the instruction execution timings benchmarking. It showed up that pretty much most of the SVE reduction instructions, the execution timings are much slower than the NEON. This is also based on the information from the ARM software optimization guide for the specific Neoverse processor architectures. So by default, SVE supports the register size in range from 120 bit up to 2048 bits. But as I mentioned, nowadays the processors commonly they implement the SVE size 120 bits or 256 bits. That's the most popular on the, for example, on the server processors and also some mobile embedded processors. So here we have the description of the SVE registers. We have 32 SVE vector registers marked from Z0 up to Z31. So lower 120 bits are shared with the NEON instruction set, which means that you can mix the NEON and SVE code, so you can access lower 120 bits of the vector registers using the NEON instruction set, and then you can use the full vector capacity by accessing it using the SVE instruction set. And here we have also the predicate register, as I mentioned, 16 predicate registers. The size is 1/8 of the SVE vector register. So here we have example of vector length agnostic programming. So we have the calculation, comparison between the scalar generic code and the SVE code. But we will not go into the details because we don't have so much time here. So this is an example of the assembly generated for the scalar generic code and the SVE code. And then we have some examples of SVE instructions. There's a lot of them, different variations. So arithmetic logic instructions, move instructions, bitwise shift, permute and count instructions, floating point instructions. So for floating point instructions, there are only supported floating point half precision, single precision, and double precision. We have some more floating point operations, so the complex arithmetic conversion, floating point. We have floating point comparison instructions, and then have some more SVE. We also have a SVE predicate dedicated instructions, so you can also execute a move and some basic arithmetic logic operations using the predicate instructions, also some data packing, unpacking, shifting and permuting. Okay, and at the end we have some information where we may find some more information about the ARM processor architecture and SVE. So this is the end. So thank you. Anyone has any questions? Yes, we have 3 minutes for questions.
Thank you very much. So while as you say, SVE is agnostic to the register length, it looks like current implementations converge back to 128 bits, right? On Grace, I think they only support 128, and I believe on Gravitons too. Maybe.
Yes, exactly. Yeah.
So what do you think? Is it like they figured out that there is not much point, or that we should expect hardware that will be actually implementing?
Actually, we have some conversations with and so Graviton vendor is AWS, so we have some conversation with them, but I cannot reveal any technical details because it's confidential. But as far as I can tell you that most of the future next generation AWS processor architectures, that they will stick to the 128 bits SVE. So currently it's supported SVE vector extension 2. So the SVE vector register size is 128 bits. Yeah. So for the future next generation processor architectures, they will stick to the same size. Yeah.
So basically, this
so agnostic model doesn't matter for those processor architecture family. Yeah.
Okay. So do I? Sorry, can I ask?
Yeah, sure.
So do I then understand correctly? As you mentioned, and I also heard that not all operations in SVE are kind of faster than on NEON.
Yes,
so
exactly.
First sub question is it actually the really latency? Is it really the micro kind of characteristic of the instruction, or it's more complicated than that because the algorithm is slightly different? And the second sub question, sorry, is, well, it's kind of probably stupid and naive, but like, yeah, how would you say in which cases would you go to SVE? Is it just if you need predicates, like really more complex algorithms, that's why, or there are cases, simple cases where you would choose SVE versus NEON?
Yeah, so answering first, can you just recall first question?
Yeah, so the speed of SVE versus NEON.
Okay, so the performance benchmark show us that the SVE code is sometimes faster, but this depends about the particular algorithm, yeah, and then of course the implementation. Yeah. So some algorithms are very vectorizable, yeah. The other not, yeah. So and it also depends on the particular implementation. Yeah. So we had, for instance, in the database engine, we had situations that for some test cases, test uses NEON code was still faster than the SVE. Yeah. So it really depends about the execution path, yeah, all the test uses conditions, yeah. So in general, yeah. So it's not only the implementation. Sometimes, yeah, some customers they have very specific requirements that they want. Let's say that for the specific function parameters configuration, they want to run it at the specific performance. Yeah. So then sometimes NEON is faster, sometimes SVE is faster. So it really depends, yeah, on the workload. Yeah.
Thank you. Thanks very much.
And the second question. Yeah.
Oh well, you kind of answered. Yeah, basically, is when do you decide between whether to write it in SVE or NEON? Is it
so? Of course, ARM says that they will still maintain the NEON. Yes. Yeah. So, like I said in my presentation, SVE is just another approach, extra vector processing you need to implement it into the hardware. Yeah. So you can still decide. It's possible, as I also mentioned, it's possible to mix NEON and SVE code. You can in C++, you can write a conversion framework, so you can convert your in C++ code you can convert the code reinterpret between NEON and SVE without any extra performance overhead.
You mean intrinsics or you
mean the most desirable usage form is using the compiler intrinsic functions. Also, if something will change at the low level, you just need to recompile the code, but you don't have to re-implement your code. So that's the best approach. Obviously, sometimes if you want to achieve the highest possible performance, then the only way is to just write the pure assembler code or use inline assembler in your C++ code.
Thank you.
We are over time. Okay, so thank you very much.